flash the as far as I can tell.
At this point, I'd like to introduce John Manferdelli, who will start the discussion off.
Let me remind you all that we're running this moratorium experiment. So
that's right.
John gets about 45 minutes of only points of clarification from you.
Uninterrupted speaking time. How's that?
No, I didn't say uninterrupted, but every question has to be prefaced by this is a point of clarification.
I will leave it up to you to crack the whip on that as well.
And Scott Charney here, he can do the objection.
Yeah, exactly. So, with that, I'll go ahead and give it to John, and thank you very much. If you got any questions or any comments, keep them moderated. If you need anything from me, let me know. Thanks.
Actually, I was telling Fred, actually, I usually like talks better when you interrupt, but he pointed out correctly that if you don't get the first 45 minutes, you'll never get anywhere. I'm John Manferdelli. There are actually going to be three of us here today. Paul England is on a hardware call right now. He'll be late. He's actually talking to the standardization group that's going to build one of the parts. So he'll be here a little late. I'm going to talk about Palladium. I'll actually refer to it Palladium, despite the fact that all the slides say NGSCB, because every time I try to say that, I transpose the letters. Let me tell you a little bit about how the talk came up. I gave a talk at the Summer Research Institute. And Fred suggested I repeat the talk and go into more detail about the actual design. Fred had a particular design point, I think, that he was interested in. I talked to him a bit about it after my talk. So we're going to structure the talk in two layers. The first layer is going to be really similar to the talk that I gave at the Summer Research Institute. And it'll probably take about an hour and a half. And actually, for all policy matters, that probably covers Palladium in enough detail so we could discuss the policy matters in great depth. And actually, if this were a course, the first hour and a half would be a great way to, if you were interested in learning the stuff yourself, go off and invent the thing yourself after the first an hour and a half, because there are lots of different design choices after the first hour and a half, and they're all interesting, and you probably don't need any more guidance after the first hour and a half. But the second hour and a half will tell you about the design choices we've made, or we think we're making, or we're almost about to make. So here we go. Oh. So let me set up why we thought up Palladium in the first place. So I'll talk a little bit about the past. Computer Security 101, the standard model, the way you protect things in security, roughly, to oversimplify, is you build a security perimeter around some trusted computing base, some code you really trust to do the right thing. And often, in the standard model, that code is the operating system, which gets installed on boot. And for some reason, you believe when the operating system boots, nobody's messed around with the thing it's about to boot. Not really a good assumption, but there you are. Then in the course of doing security computations, trusted computations, you authenticate some security principles. And the prototypical example in the time-sharing days was the actual user who authenticated himself by typing in a password. Today, that's actually changed quite a bit. The kinds of principles you authenticate are not always users. For example, code is probably the most important principle these days. And you trust that the authentication procedure is right, A, because somebody's investigated the guts of the authentication procedure, and B, because it's happening inside this security perimeter, so nobody's messing with it. Then you authorize or deny actions based on the security principle making the request, and the access rules for the resource you're trying to get access to. So the resource might be a file in time-sharing days. It may be the ability to talk to another process on the same machine. It may be the ability to communicate with someone. And then finally, the great advance, I actually should have said the past is prologue. Palladium really builds on a lot of great inventions. one way to think of Palladium is a small change and integration of a bunch of them. And probably the biggest change is sort of just how we think about security and cryptography. And I'll have I saw Gene Spafford, who I've never met before. Yeah. So I'm going to have a quote from you in a minute about encryption. But part of the basis of why we can do that, why we can do what we do, is actually enabled a lot by public key cryptography. So back in 1972, when people were doing multics, they could not have gone down the path we went. Or I guess they were doing it a bit earlier, but that's when they wrote the book. The second sort of setup is that we usually think of principles like users and machines, but we forget that in almost all cases, software is acting on our behalf. So one of the key things we pay attention to in Palladium, one of the sort of ahas, is that software is ultimately a thing you have to concentrate on for security. And there are a few comments about software. Our reliance on software is increasing, and that's a good thing for Microsoft, right? The more people rely on software to make their lives easier, the more you use software, the better we like it. You can't beat software for flexibility and features. It's hard to beat it. You can put new features in quickly. In fact, one of the things I'll talk about is how we have to resist the urge to do that. On the other hand, software is usually run by an operating system. And current operating systems, and I mean all operating systems, are brittle. Once they're penetrated, you can't know what's going on after that. Everything is suspect on the machine. The trust relationships in a connected world are much more complicated than the trust relationship we had in the time-sharing days, when there was an administrator who was trusted, and actually, for God knows what reason, given the administrators I know. But they were trusted, and they knew the users, and the trust relationship was pretty informal but well defined. Now trust relationships are complex, they're dynamic, and they change, and they're brief. When you buy something on the internet, things change. And sometimes, actually, when you employ somebody to do something for you, it's briefer than we used to think of in the old days. And we have increasing, but few tools to make sure software is doing what it's supposed to do. OK, so here's the Gene Spafford quote. Actually, I'm a little bit unused to this. I'm not seeing my own slides the way you see them, but here it is. Using encryption on the internet is the equivalent of arranging an armored card to deliver credit card information from someone living in a cardboard box to someone living in a park bench. And I hope you actually said that, because last time I gave the talk, I quoted you, and I wasn't actually sure whether you said it. And one of the points here is encryption is not the problem. It's not typically somebody. We know how to do encryption. We know how to do wire security. The trouble is, at the two endpoints, everything is a mess, and it's very difficult to tell whether you're safe. In fact, if you're interested in wire confidentiality, it's pretty easy. Once you've encrypted the thing, and take it offline for a minute, encrypt it, send it over the wire, you're pretty sure. You can be pretty sure, modulo the cryptography, that nothing bad's going to happen. But that's not where the bad stuff happens. Where the bad stuff happens has to do with how we establish security perimeters. Security perimeters are pretty fat, and they're around the edge. And they usually enclose tons and tons and tons of computations. And any one mistake in there is a disaster. It's a potential disaster, sorry, not necessary. Fortunately, not everyone is a disaster. Otherwise, we'd never get anything done. And the second part of the modern problem has to do with how people can exploit that disaster. In the nice time-sharing days, the worst thing that would happen was the guy in the next room who you knew would, sort of play a joke on you when you're, editing a file or doing something. But over the internet, for two reasons, things are much more dicey. One is they're not your friends, and secondly, you're relying on some important computation, something that's important to you, and you do it frequently. So one sort of problem is that the security perimeters are thick. They're established once, and they have to endure over very long periods of time. And that's actually kind of a problem, given the modern state of technology. So we're sort of faced with a Hobson's choice. The first choice is, OK, we give up on building flexible computers. We'll build these nice closed systems and where you can think of the entire hardware package as the thing that's the security perimeter. You don't load new programs into the device, or you do it under such constrained circumstances that you don't think of it as a programmable computer almost. Perhaps the only software is software approved by the manufacturer. They're fixed function, though. Because they're so small, they usually only do a few things. On the other hand, they have this nice property of having a small trusted computing base. And if something goes wrong, you hit a switch and reboot them. And they don't have to load every DLL in the world. They possibly come back quickly. OK, and the second option is an open system, which I'm kind of a fan of. Their general purpose, the bad thing is they have a big TCB, and as a result, they're fairly permeable. But they have lots and lots of flexibility. And actually, that's an important economic point. And the economic point is you can buy a PC and not know all the things you're going to use it for in advance, but be pretty confident that some program will come along that's important to you and you want to run in the future, despite the fact that you don't know about that program today. OK, so we picked both. We like the advantages of both, not a surprise. And our choice for both is a trusted open system where you can dynamically erect a security perimeter. And I mean now a real security perimeter that we think has a strong argument for not being penetrated. Because it's an open system, all the software on the machine cannot be trusted. So the sort of back of your head intuition is the effective TCB, the software you rely on for critical computations, is small. And that's what the security perimeter is erected around dynamically. That the security perimeter has high assurance. And assurance means not only the inability to observe it or interfere with it, but the inability to modify code, to be sure that what you've loaded in is what you've expected. One thing we tried very hard to preserve about open systems is that any OS and any application could run. We did not want to be in the business, probably for the people in the group, partly just our own beliefs, but it probably fits in well with what people think generally. We didn't want to be the guy saying you have to run this software at this time, otherwise the hardware is useless. It doesn't work. So we wanted any OS and any application to work. We wanted it to be general purpose. If you had a great new security idea, we wanted you to be able to just write code and do it, and not have to build a piece of hardware and wait 4 years to the hardware to get out in the marketplace. On the other hand, for the trusted computations, we wanted behavior that was predictable. And I actually stifled the urge to put the word correct, even under adversarial attack. And I'll define what adversarial attack means. So that was sort of the background, what we are. So let me do a little plug for MSR. Palladium actually originated out of MSR. There was at least one major contributor outside MSR, and that was Brian Willman from NT-Base. But most of the work started when we were here. So the organization you're helping to make better, help make us all better, at least if you think Palladium was a good idea. OK, so what is it? NGSCB is a bad name for this new security technology, and we'll change the name soon, that uses unique, and I mean unique in the sense of the way it's integrated. Parts of what we did have been floating around as ideas for a long time. And it's a new kind of security model to guarantee a certain well-defined integrity, confidentiality, and trust negotiation interconnected world. And this is sort of a key point. If the world were not interconnected, why you do this, aside from it being an interesting thing, would decrease. Not go away, but decrease. OK, what were our security goals? It was not to protect everything in all cases against everything. It was to protect data processing against software attack. Let me say what software attack is. Software that comes on your machine, whether or not you know about it, that misbehaves and may affect a trusted computation, a computation you're relying on to work accurately or predictably. a strong way to authenticate machines and software, because after all, if you can't authenticate the machines and the software, you can't remotely know whether you should believe the computation that's happening. Provide compartmentalization, isolation we call it. Actually, we've used 5 names, that none of them like it, for secure applications. And that's this notion, and when I describe how Palladium initializes, you'll see what this means in sort of graphic detail. But the short version is we can dynamically erect security perimeters about small pieces of code, comparatively small pieces of code, and not rely on the entire operating system having to be safe. And finally, once you've done this, there's a sort of safe haven for computation. So if, for example, if you had a small trusted program running that could monitor the health of the machine, and you were sure it wasn't going to be penetrated, you could use that to recover from other kinds of attacks and rely on the fact that that program itself was not subject to attack. OK. That's the sort of background. So there are four key functions in Palladium that make the whole thing work. If you have these 4 functions, you can let your imagination run wild and do almost any security processing you want. The first function is this strong process isolation, the ability to load in a piece of code, a known piece of code, or put a security perimeter around it, and have nothing, not even the operating system, be able to interfere with its computation. Or Jim Whittaker. None of them. Sealed storage. Once you have strong process isolation, you need the ability for programs to preserve state over activations. So they need to be able to store things that they can rely on between computations. And actually, they not only need to be able to store it, they need to be able to store secrets that let them authenticate themselves to other programs, other whatever else you want to authenticate yourself to. Seal storage. The third component is a secure path to and from the user. And actually, I mean something very specific. I mean the path from the user typing in to a program or moving the mouse to a program to the actual small trusted computing base he's relying on, and then back out on the screen. And this is to avoid the obvious attacks of password snooping, that sort of stuff. So you should be able to know that the keyboard strokes are not being stolen by another program, and that what you see on the screen, which affects what you're going to authorize, is exactly what you expect to. Oh, sorry, exactly what the program says it is, what the trusted program says it is. OK, and the fourth one is a little bit more abstract, and it's the only semi-abstract concept, really, and that's attestation. Once you have the security perimeter, once it has its own secrets, the way the trusted computing base expands in a controlled way is one trusted computing base can prove to another trusted computing base who it is, so they know they can trust each other based on their software identity. And they can exchange keys, then open up a secure channel. And now you have 2 trusted computing bases which can act in conjunction. So attestation is the ability of one program to prove to another, either locally or remotely, over the internet, over any way, that its identity, and to couple that proof with information that the receiving program knows comes from that program. That was a mouthful, but that's it. OK. So, actually, I should have mentioned one other motivation in the past this prologue, and that is probably if we came along and said to Microsoft, we got this great idea to make everything secure, it only really is believable if you have small programs. So why don't you dump the rest of the operating system, get rid of all the major applications, and let's start over again? That probably wouldn't have worked so well. And not only wouldn't have worked so well from our point of view, probably wouldn't have worked so well from our customers' points of view, who invested a lot of money in building all this software and seem perfectly happy in many circumstances with how secure it is. So we had to do something which literally would not affect any existing program. And actually, we also had a slightly selfish motivation. We didn't want to get in the middle of the software stack in a way that affected which affected how the test cycle would be impacted by new code. So for example, no matter what change you make in the main operating system, if it can affect the main operating system and its applications, it's subject to months and months of testing. There's a huge delay in getting that in. And we want it to be nimble enough not to worry about that. So the idea was roughly to carve the computer up instead of to 2 quadrants, is to 4. So this is the normal kernel mode, which in the old days was the trusted computing base, and user mode. And what affected it being the trusted computing base is there were tons of things that people could load in here. You couldn't be sure that you booted the operating system you thought you booted. If it was a user application, there were tons of DLLs that weren't built by you. So, you got tons of flexibility from people, but you weren't absolutely sure of your configuration. So what we did was introduced another mode. And it actually, just as in the old days, it has a kernel, a security kernel, which we call the Nexus, and user mode applications. Now is as good a time as any to talk about some of the restrictions, though. This is the place where you put the drawing is not made to scale. The Nexus is a comparatively tiny piece of code. Think Unix version 7 kernel, 50,000 lines of code. And is not supposed to change frequently at all. Does not have loadable device drivers. Can't load a device driver in there. The agents, or the trusted applications, can be as big as they want. But obviously, the bigger they are, the less you may trust that they're going to perform exactly as you expect. But the key thing is nothing on this left-hand side can see anything on the right-hand side. Applications are assured hardware isolation from each other. And the Nexus has access to secrets that are only available to it on that platform. And it can do the same thing for the user, for the application program. So this is the 4-quadrant diagram. Will this just go on?
I have a clarification question.
Yes.
Are you going to say what the other boxes in the top of the Nexus are?
The trusted user engine and the runtime. Yeah, let me talk about that briefly. Marcus and Paul will talk. This is really a kernel. It's the thing that gets booted. Even in this restricted environment, we don't expect you to make up your own libraries for doing printf and talking, and opening and doing the sort of grunt work of opening an IPC channel to somebody else. So there's a runtime, which you can think of roughly as the C runtime, probably smaller, that we provide. That's part of the trusted computing base that you can use to build applications. So that's that. What are TSPs?
Well, I think you can sort of imagine this right-hand side there as a microkernel, and these TSPs are essentially user workspace. I think it stands for Trusted Service Provider.
The agents are the actual programs themselves, and Trusted User Engine is yes, sorry. You could just scream out.
Clarifying.
I'm going to release you from the bond of not interrupting.
You've left the network port on the left side.
All the network ports are on the left side. All I/O is done on the left side, except the trusted user input and trusted user output. So the way of doing I/O on the right-hand side is you encrypt something, give it to the left-hand side, and you just make believe you're sending it over the internet.
So you have not, to clarify, we do not have a trusted path from the network port to right-hand side.
That's right. The way you trust that is encryption or authentication, not I know that the hardware from me to the guy on the other machine is okay.
So the spirit of clarification questions.
This is getting, all right. All right, Fred.
It's a clarification question disguised as a clarification.
Yes, that's okay.
When you said hardware partitioning, does that mean all scheduling, all cache access?
It's a great idea. One of the reasons, actually, it's a great question, and it wasn't a point of clarification, but it's still a great question. So when we talk about how we might have designed this, they really could have been literally almost as if these were 2 separate computers. This guy had his own scheduler. We actually didn't do that in the first version. Scheduling is done on the left-hand side. So in a few slides, I'm going to explain to you one of the attacks we do not guard against is denial of service attacks on the right-hand side. Right? You can turn off the computer. You can do whatever you want. But we rely on the left-hand side scheduler, and there are two important reasons to do that. The first is we try really hard to keep the code base small. So we fight like hell every time there's a new feature that somebody wants to stick in. A scheduler is a new thing. There's more code. And you have to tune it. The second thing is that the second reason has to do with what I said about interfering with the left-hand side. The left-hand side applications were built under some scheduling assumptions, which grew up sometimes implicitly, just because the left-hand scheduler does what it does now. And we didn't want to break those applications. And the third reason was fairly selfish. The guy who does the left-hand side scheduler is pretty good. And we might not do as good a job on the right-hand side first version. So scheduling, well, we obviously have to have our own thread management on the right-hand side. Scheduling is something in the first version which is left to the left-hand side. The left-hand side schedules us as if we were a normal process, roughly.
Same thing for caches.
Huh?
And cache access.
Yeah, so the cache, we'll talk about that. Another good question. Yeah, roughly, when we come in, when we go out, I'm anthropomorphizing everything. When the right-hand side goes out, it has to make sure the caches are clean from all private state. Gone. Wipe it out in one way or the other. Okay, I talked about this. Attestation extends the TCB. Let me sort of explain how this works in a way, because it will have a bearing on some of the privacy questions. Policy questions we might ask about later. You have two trusted programs that started up on two different machines, one in San Francisco and one in New York, and they want to collaborate in a secure computation. So here's what they do. Program 1 asks roughly the hardware to sign a certificate. The certificate says, here's my public key, here's the cryptographic hash of the program I am, signed the hardware. And with that, he sends the certificate which accompanied the hardware from the hardware manufacturer that would persuade the other side that it's secure hardware. So now the other side of that computation can actually be the same program, looks at the certificate and says, oh yeah, I trust that that's this program. It's isolated. I know nobody else has the private key associated with this public key, because I know the way this software is constructed, it manufactured that private key just before it sent it to me, and it didn't tell it to anybody. And incidentally, between activations, it's going to use seal storage to save that private key. Okay, then the second program does the same thing. Makes up a new private public key pair, puts the public key in an attestation state, and sends it to the left-hand side. Now they both have certificates. They both trust. They both have public keys that can open up secure channels. Everything is hunky-dory, and you can proceed with your trusted computation. You only actually have to do that once, because once you've established this trusted key pair, then you save the private keys you've generated in the application, and you can rely on them from then on until you decide you want to refresh them. So there was no central authority. I mean, you can think of the hardware manufacturer as a central authority, but the software made up its own keys. There was no big certificate CA infrastructure. That's it. And I just said that. So I just said in words the second major bullet. Now, as I've described it, there's a potential privacy issue. Right? The privacy issue has to do with the fact that I attached the machine certificate to the attestation statement, so you could believe the private key which signed the statement came from an authorized manufacturer. So there's a public key which identifies not the person using the machine, but the machine. That public key is unique to the machine. Actually, just as a preface, I've gone to the last point without doing the middle one. The protocol I just described is not complete. The way I said this at Cambridge is don't try this at home. The actual protocol is more complicated. You've got to be careful of replay attacks and a bunch of other stuff, but that's not terribly relevant at this point. What is relevant is that you can replace that protocol with a zero-knowledge protocol. It's much more expensive. And the zero-knowledge protocol achieves the following. There are two related secrets inside the hardware, which neither of which are disclosed, but they're related in a well-known way. And the zero-knowledge protocol can attest to the fact that this blob that you just sent over the internet, that's a public key, came from a trusted machine, can't tell which trusted machine, with the class of hardware you expected, manufactured by a trustworthy manufacturer without disclosing the machine identity. So in the end, you don't put the second certificate that comes from the machine manufacturer, which discloses the identity of the public key. It's a much more expensive operation. It's thousands of times more expensive. And it's a probabilistic algorithm. So basically, roughly what you do is you say, I'm going to prove to you that I'm on a trusted program with probability less than, with a probability whose error is less than 2 to the minus 30 or something, 1 in a trillion or a billion or something. And you just decide what threshold you're willing to live with.
When you say thousands of times more expensive
per attestation. So a typical attestation would happen a few hundreds, tens of milliseconds, and
expensive in time.
Right?
I just wanted
Well, and actual computation too, and a zero-knowledge protocol, the ones we know, take seconds of computation.
Question of clarification.
Yes.
When you say may be replaced by, do you mean you're thinking about replacing it with? Or?
We'll talk about that in the policy. So what and we'll talk about that in the hardware. The hardware is being, when I describe the hardware changes, which again now is as good a time as any. In fact, Fred, I'm going to lift the band because if that's okay with you, the band is lifted.
It's been killing me.
It's okay. I like it better. I feel like I'm.
45 minutes.
Point of clarification: did you actually lift the band? Okay. So let me tell you the hardware changes first, and then I'll tell you about the zero-knowledge protocol. In order to pull this off, we have to make several hardware changes on the CPU. We have to change the CPU, which will affect the boot of the Nexus. They have to change the memory subsystem, which provides the hardware isolation that I talked about. We have to change the GPU to make sure we have a trusted output path. And we have to change something in the input. Let's just make believe it's a USB hub. Graphics processor unit, the thing that, the card, the video card, roughly. And we have to change the trusted, let's just say call it the USB hub for input. So those 4 changes. Now, we need those things. They just increase the number of transistors on those. They're not a big deal. They're not, in the end, going to cost anything.
They're still on the left-hand side.
The hardware, there's no left-hand side for hardware. The hardware is the hardware. Yeah. So, we have to make 2 more changes, which do cost money. And actually, one of the motivations was to make the price of those changes as small as possible, because if you've ever talked to an OEM and you say, I want to change the price of your motherboard by 3 cents, it's like you wanted to steal their children or something. The first change is there's a new part which has to do the cryptography involved in booting the Nexus. And that roughly corresponds to doing some private key operations and storing keys for that Nexus. That's a new smart card-like chip. It's pretty cheap, right? Smart card cores are pretty cheap. And it has to be soldered to the motherboard. It's not replaceable. You can't take the smart card out because it's proving what the platform is. And those have platform, that has cost. Now, when I get to how the software is structured, it's the old story again, the past is prologue. The hardware provides sealed storage, attestation, secure path, and isolation for the Nexus. The Nexus provides the same benefits for the agents, the trusted agents. And in fact, the public key operations happen really rarely. Roughly, you can think about it, happens when the Nexus initializes. So they don't even have to be fast. They can be dog slow. The attestation, which is affected by the hardware, has to do with how you would obtain hardware keys. And now to get to your question, what we're trying to get into the hardware specifications is there are 2 methods of attesting. One method is the simple, fast, dumb, potentially privacy violated. I don't know. I hate the word violating, but the bad one. And you know what? That's great for most things. If you're using it in an enterprise, what the hell do you care whether somebody knows? And if you're using it with your bank for sure wants to know who you are. So that protocol is great for that. And then we're going to have a separate second way of authenticating. And basically, it's the same story I'm about to tell you. Both sides of the transaction agree what kind of attestation they want. If you don't trust the zero-knowledge protocol on the right-hand side, say, look, I don't go for that. You have to do the other, but you pick it. So both. There will be two parallel ways of attesting in the hardware. And in the software, there will probably be even more. So user choice. You're doing a trust computation. We basically let both sides of the transaction negotiate what they're willing to put up with and just enable that. So in the hardware, there are two.
Question, not of clarification. You could
No,
imagine,
you can stop that now.
Yeah. So you could imagine something in between, right, where you get a temporary key from a trusted
Yes.
party and so on. And so you don't plan to support that.
Well, no. The first idea for the privacy thing was to do that, actually, was to set up these identity services. And I think, Mark, are you going to talk about that a bit in yours? Where you attest to an identity service. You make up your own private public PKR. You do this normal dance of attesting to this third-party privacy-enhancing thing. And they sign the certificate over their private key that says, look, I've gone through this dance with them. This public key actually comes from a trusted program. And you're kind of going to rely on them then. But the normal statement is, the normal thing would be, okay, well, why isn't a government going to go subvert that or whatever it is? But we could do that, and we will support that in software. And I think, is there support in hardware for that, for the identity? Okay. So we will support that in software. But we wanted to drop, we really would like, although this is actually costly for the smart card core guys, we'd like a method where we could say, look, you can use all this stuff without ever having a privacy problem. The other thing I should say is, you could use all these functions independently. You could use the isolation, the trusted path, sealed storage, without ever using attestation over the net. In which case, your privacy is just fine, also. So, anyway.
All right, Chris.
Good.
Sorry. I mean, some of this sounds an awful lot like TCPA.
It is. I'm sorry. I should have said that. The smart card chip.
Sorry.
Yeah, I'm going to call it TC. I'm going to use the letters. And
Way back at the beginning, you made up this is all MSR and
yeah.
I mean,
TCPA actually grew out of stuff we did back in the 1997, 1996. We actually were a founding member of TCPA, too.
that may well be true.
Yeah.
I wouldn't dispute that. But nevertheless, the other people I talk to at TCPA don't say, well, MSR did all the stuff and we just copied what they've done.
Yeah. Right.
But nevertheless, you would claim it's all your idea.
Well, people collaborated on the spec.
Yeah.
But I think the way the rubber meets the road is the following. So TCPA is morphed into TCG. I'll talk about that
Yes.
another
Yeah.
day. So TCG will be a standard. And the people contributed to the standard will have to make an IP statement. And I think in the end, you'll see is the IP statements around seal storage, attestation. That's probably it. The main things will actually be Microsoft IP, which, now, that's not to say the other people didn't contribute. It's not to say they didn't have similar ideas at some time. But it was sort of a funny story. I'll do the TCPA, TCG story. And actually, TCPA was a compromise for us. That smart card chip, the TCPA version 1.1, doesn't do everything we need to do. But the TCG, the morphed organization, TPM 1.2 part does do what we need to do. And that's the one where right now Paul is undoubtedly trying to get direct proof in the spec. Direct proof is the privacy enhancing protocol. Sorry, I mean, yeah.
Can you associate a machine or a program with an IP address to this IP session?
So, again, we don't do any I/O. We say basically that all these protocols are we're going to hand something to a channel. We don't know how it got established, why it got established. So if you were worried about being tracked down by IP address, you have to do more. And actually, you could write a trusted program to make sure that more stuff happened.
Right. But the answer is no. So the machine can change IP address.
Yeah, you bet. Do whatever it wants. It can do spread spectrum, send the stuff over a radio for all we care for attestation. Okay. I'm sure this is probably preaching to converted. Just because you attest to something doesn't mean the code quality is high. It just means it's the code you expect it to be. There can still be mistakes in the code. You still have to make a trust judgment about whether you trust the code that said whatever it said. It could still be malicious. It could still have bugs. The story for attestation, just as everything or largely everything in Palladium, is that it leaves the judgment about whether the trust links to the other side. It's not, there's no central authority. When you do an attestation with somebody, you look at the hash, you can identify what program that hash came from. It's your judgment, roughly, whether you trust that program. Now, before somebody asks a point of clarification and says, well, how can my mom know whether to trust the program, which is the normal question I get at this point, we don't expect every user of Palladium to inspect all the source code of the programs they use, verify that they've compiled to the same binary, and then check the cryptographic hash. So largely what we expect is a trust network. And actually when Bruce Schneier heard a version of this talk, he did the, wow, how does my mother going to know to trust it? And my answer to Bruce was, Bruce, you're going to sign a certificate with the hash that said, I looked at this code. I think it's OK. And your mother is going to defer. Her policy, her machine policy is going to defer to you and say, look, if my son said it was OK, I believe it. And there'll be lots of organizations. I hope there are lots of organizations that do that. We'll see. OK, what runs on the left-hand side? Windows as we know it today. Applications and drivers still run. The marketing guys hate when I say this, but viruses still run on the left-hand side too. And the right-hand side can look for the viruses for you, but they don't a priori stop viruses from running on the left-hand side. Pretty much the goal was any software that runs today on a PC runs on the Palladium PC, whether or not Palladium is running. There are tiny minor exceptions with some hardware debuggers, which will make work, but you may have to actually change something for some class of hardware debuggers. What the right-hand side needs, there's a coordination dance between the right-hand side and the left-hand side, right? The left-hand side gives up physical memory and can't use it. Can't look at that memory and has to know not to try to touch that memory. Otherwise, it's going to see a bunch of zeros or an exception is going to get generated to the right-hand side. So there are small memory management changes to the left-hand side, so it will give up physical pages. There's also small changes to the left-hand side to have shadow processes that are scheduled for the right-hand side. To say, right-hand side, I've given you a quantum of time.
This takes place during boot, so the Nexus boots first?
No. I'll talk about the Nexus boot. The Nexus can boot anytime, can get torn down, can get booted again. But there is a coordination dance between the right-hand side and the left-hand side about what physical pages are available.
The right-hand side is protecting against the left-hand side's boot?
The right-hand side is protected against the left-hand side messing with it, yeah.
So would you add mentally to the list of things that you're going to address why there are only two sides?
Yes. And actually, Marcus and Paul are going to talk about that in more detail. But I bet if we don't, you'll ask about it when we're all done.
And we say you do it when you want to do it.
Yeah, okay.
When I want.
Yeah, okay. There's some memory Yes.
I have one question actually. Wouldn't this coordination introduce some covert channel?
Oh yeah. There may be a covert channel.
Yeah.
You've got to. So, if we were trying to make the right-hand side what we would call in the old Orange Book A, or very high security, there's the hardest part. We've done most of the. This is safe enough for almost all commercial anythings, but the hardest part in any analysis is covert channel analysis, and it's virtually impossible, really, to be sure that there are no covert channels. Although, as I said, for reasons I'll explain, the user of the machine, the hardware, the person who actually controls the physical hardware, knows exactly what programs are running, in fact, controls it. And to the extent you can control covert channels by what programs are running and knowing what they're doing, you can do that. That disallows that. But covert channels, I would never say after a 10-minute analysis you'd be sure there aren't any of those. Yeah.
Well, but you can't say that there will be.
Yeah, you could probably say there will be. That's right.
So why does, I mean, you elected a design choice that has the right-hand side making demands on the left-hand side. If you had built a virtual machine manager and run the both on top of it, then neither side would make demands.
Okay, so I'm going to try to answer your question now. Then we'll go to and they'll talk about this. The thing we call the right-hand side can roughly be factored into two pieces. And the one piece is really a virtual machine manager. And the second piece is the thread management for the local system, for the guest system. Part of the reason, so in fact, if you wanted to, in some future version, that first part, that top part of the stack, actually could be working in conjunction with a real virtual machine monitor. Let's call it Connectix for a minute. And then you can run a bunch of guest operating systems and think of the top level thing as the nexus, the virtual machine monitor as the nexus. We didn't do that in the first version for a couple of reasons. Usually the answer to all questions is of why didn't you do that was code size. The more we do early, the bigger the code is, the less we're sure we did an okay job.
That's actually not what he means. He means a virtual machine monitor for both Windows, for both.
Well, if the top level, so you can't virtualize the Nexus. You can't. Right. So if you're going to have virtualized machine, you have to have the roughly the Nexus functionality described before.
Well, when he asked about virtual machine, he thought, I believe, that you have a virtual machine monitor below Windows and below the Nexus. This is a different architecture.
Yeah, you can't. So you cannot do that.
Right. You partition them.
You have to partition.
And on the right side, you have a virtual machine monitor version 2.
That's right. That roughly, that's And the second reason has to do with hardware. Virtual machines typically virtualize all the hardware. The only hardware we care about is this trusted input and output. Everything else, we're not touching them.
I still don't understand the motivation for not having processor control in the sense that scheduling is still done.
Because there is no common virtual machine.
I mean, I can understand that.
So, again, it's purely pragmatic in the first version. We don't want to mess with the left-hand side scheduler. We don't want to break applications that the left-hand side relies on some underlying scheduling mechanism to make sure it works right. We don't want to write a scheduler that we tune, and we don't want to have to add the scheduler code to the right-hand side, because the mantra for the right-hand side is small, 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 small.
Well,
you may not think that was,
How much should the scheduler be in terms of the number of instructions relative to the Nexus?
Actually, a couple thousand lines for the scheduler, maybe. But it's stuff that's tuned. Yeah, but it's stuff that gets tuned all the time.
I don't know. I don't buy that, but that's okay. I mean, the architecture is fine.
Okay.
Yeah, I have a few more slides on.
Yeah. I actually, to tell you the truth, there was a little bit of a fight about that. I and another person who was actually not from research actually wanted to put a scheduler in, but
Here's another.
Again, minimalist was what we went for.
A different architecture would have been hardware-based, a completely different CPU for executing the Nexus code.
Yeah, it would have been, but okay, putting a new CPU certainly changes the price of the old.
Fair enough, but there's now a serious lack of control over the critical resource,
which is
the CPU.
The schedule.
Yeah.
Yeah. So you can certainly imagine an architecture that did that. And again, our goal is sort of the old thing in security. You got to go back to our attack thing. We were not in the business of protecting against denial of service attacks. We thought that was just, we weren't going to do that. Our attack model was software attacks. And we didn't want to increase prices too much, and we didn't want to say, here you have this extra CPU that if you use sometimes. The nice thing about this architecture is you get to use all the hardware you paid for at full bore. If you use it for trusted operations, it runs at full bore. If you use it for untrusted operations, there's no extra hardware, kind of, except for this little stupid smart card core. So you could say that was a bad idea, and maybe if I was willing to pay another couple $100 for a machine, I could do something which actually helped with denial of service attacks. Although if we do Fred's virtual machine monitor and put the Nexus on there, that it could. I mean, you could add denial of service to the list of things you're trying to protect against. But the reason is purely practical. Don't add cost. Don't make the thing big. Don't take on too much at once. Don't try to virtualize every piece of I/O that you're doing.
Your characterization of the attack model as we're doing software attacks but not denial of service attacks is not a good way to say it, since software does do denial of service attacks.
So
it seems like you're doing safety but not liveness.
That's right. Yeah. There are too many adjectives to say it right. I'll try to say it right. You're right.
Safety and liveness.
Yeah.
It seems like the other thing is this is I have a sense this is just the first shot, and this is something you expect to evolve over time.
Right. And the important thing, again,
it sounds like it's going to get bigger over time.
Again, we have to be careful of that. So again, one of the reasons for the virtual machine approach is to draw the line at the virtual machine and say that's never going to get significantly bigger. If you want to screw around with the trusted silos, they may get thicker, but at some point we'd say that's not our worry. It's a little bit of a cop-out.
Well, wait, I didn't follow your answer. I think what you just said is if we adopt the virtual machine manager approach, we don't have
in the future. Then we have a defense against saying that part that we write has to get thicker, significantly thicker.
But that's an argument for virtual machine.
Yeah. No, it is. It is. No, it is. What I'm saying is, in the future, one way to use the hardware is to have the virtual machine monitor use the Nexus, do exactly what you're suggesting. And if you do that, the virtual machine monitor, with some thickening, not much, actually, you may have an argument for it protecting against denial of service attacks. And that would be the right thing to do.
So then if that's your line of argument, we should at least have in the back of our minds looking to make sure you're not doing anything now that's going to make it difficult for you to take.
Let me introduce the back of my mind who's going to talk about that. We're thinking about that.
That's a very naive question. When I think of scheduler, when I think of scrubbing policies or any policies that separate the left or right hand side, the policies are being still maintained on the left hand side.
No.
Scrubbing policy, let's say for the cache, will be still maintained on the left hand side.
The which policy for the cache?
Let's say scrubbing of cache.
No. When we leave, we get to scrub the cache. When the right hand side leaves, it says, "Okay, left hand side, you get to take over again." We scrub the cache. The left hand side certainly controls the cache while it's running.
All right, I was going to a more generic question within the sense, are there services kept on the left-hand side which control when the right-hand side is in mode? And,
yes.
And let's say during boot up processes or whatever on the left-hand side, you're more susceptible to those being attacked and convoluted.
So I'll describe the boot in a minute. So I want to defer part of the question until I describe how the Nexus initializes. But so 2 points of the question. It should never affect the safety of the Nexus. The left-hand side should never affect whether the Nexus safely boots. It can affect whether it gets booted. It can interrupt a boot. But once the thing is booted and somebody signs an attestation, you should be able to 100% rely on it. Doesn't matter.
So by default, the right-hand side has certain, let's say, safety structures which...
The hardware and the left-hand side software is supposed to guarantee safety.
So maybe you'll talk about it. The window manager seems like probably the hardest thing.
It's hard, yes, that's right. That's right.
So we
and I'm not sure that is totally baked. Exactly.
It's hard because if the right-hand side needs access to the window.
Well, there are a lot of reasons I can imagine. First of all, modern GPUs are complicated, so you might have to have a core minimal interface.
Yes, that's exactly. In the first version, in our first version story, you're not going to run for right-hand side operations. You can't run the GPU at full speed. Yeah. The billions of lines of code that they put in the GPU are not going to be available, so it's going to be much simpler.
So in some sense, the architecture for the GPU is also going to have a sort of a
creeping
conceptual split.
Yes. That's right. That's right.
Yeah. So what I wonder is, does it not make sense to just fold that into the hardware components?
It may, but so let's defer that discussion. It's an important thing. So there's this. Until we get all the issues on the table, it's hard. There's this ugly interplay between economics, making things expensive when they get the thing out, when you get the first big application. So we took a design point. I can guarantee you it wasn't frivolous. We thought about it pretty hard. But cost, the highest priority thing was whatever we're going to do, we wanted to say was safe, period. Safe. And probably the second order bit was don't change the cost too much in the first version.
So are you going to at some point talk about applications that will be attracted
Yes.
to this first version?
Yes, I will. I promise.
My other concern there is that that's the one area where I would see creep for code bloat.
Is in the application?
The window manager coordination.
Oh, yeah. That's right. That's right. Actually, we run that as a user process now, right? The current design.
Yes,
But it could still creep. When I talk about the how we boot, I'm going to talk about what the actual TCB is and what design choices you have to.
Excuse me, when you say that there's going to be slow output, the trusted output model is not going to be as fast.
Yeah, so roughly the trusted output model is we get part of the screen and we get the bitblit from memory onto this protected part of the screen. A lot of the processing that GPUs do now are not available to us in the first version.
So are you also saying there's reduced functionality for the
No, we can bitblit anything on the screen. If it can show up on the screen, we can put it there. But we have to do all the computation on the right-hand side.
It won't be accelerated.
So it'd be like there's no graphics unit. Is that the argument saying?
It's almost like there was no right. That's right.
But I'm sorry, who are you using for just putting up the text?
The way to think of it, and I'm not sure you can, is inside the right-hand side memory, we construct a bitmap. And if you stick that in the frame buffer and don't touch it and just display it from the frame buffer, the text is there.
Got it. So the right-hand side constructs the bitmap.
Yes, roughly.
Isn't that a huge project if you want to do all the fonts, do all the graphics?
No, we don't do all the fonts and all the graphics.
So how? So
it's more limited.
I'm missing something very basic here.
Yeah.
So how is it that you construct this bitmap that contains the text that the user will see and can trust? If you don't do the fonts and the graphics and so on.
No, we do, but we don't do all the fonts Windows have. We don't do all the graphics things Windows has.
So there is a reduced functionality on the output.
Yeah. Okay, so I guess I'll try answering. The hardware in principle can display anything. What our right-hand side software does in the first version will be restricted. You can't do all the things. Now, restricted in the following sense. I could stick a trusted application that could do all the processing you're telling me about and say, please display this on my trusted screen. That could certainly happen. But we're not doing that.
Thanks.
Sorry, I might have missed something. I still don't quite understand how you can really trust what you see.
I know.
Because the graphics card is presumably a bog standard graphics card.
No, it's not. No, they have to change.
You have to use a special graphics.
Yes.
So I can't go and buy my. You need two graphics cards?
No. So when you buy a Palladium machine, it will come with a graphics card, which is Palladium,
So I can't run games on my Palladium machine.
It's going to be a version.
There's a version.
There's only two companies in the world, right? So those two companies are signed up, right? So,
oh, okay. So basically there'll be a place.
But to go to his question, you probably won't play very many games on the right-hand side, or you'd be sort of discouraged about the.
No, it's just that when my son's machine breaks, he wants to come and use my secure machine.
That'll be fine.
Okay.
Yeah. Okay, so this sort of goes to why we would build such a machine and what applications would get attracted to the first version of the machine. And actually, a bunch of policy questions will come up here by the time I do the third slide, I bet you. So, secure real-time messaging, secure mail, and secure distributed processing are three. Let me tell you what I mean by secure distributed real-time messaging. So if I were about to have a conversation with my lawyer on his computer, between my computer and his computer, right now I can have wire confidentiality because he'll have a private key, I have a private key. But I am certainly not protected about whatever wacky way he set up his machine, whatever viruses he has on his machine, whatever dopey things, or accidentally or because his machine has been attacked, the state of his machine. If he were running Palladium, I am actually unconditionally, he may not actually finally get to see the screen I put up, but in the conversation, my stuff will never get leaked because there was a software attack on his machine. So, secure mail, the same thing. Secure distributed processing, web services can actually be negotiated between people who never talk to each other. And you can be sure that whatever the program says it's going to do is going to get done and nothing else, even if the guy who operated that program is not so crazy about you.
1 second. I mean, just secure mail and secure distributed processing both would require somewhat more functionality
In the application level. Yes.
Than
Yes.
I mean,
Yes. So we will probably, again, we're still in the midst of we will probably do a real-time messaging application. When you buy Palladium, that's one of the things that when you buy Windows, sorry, that'll be and secure mail.
But the UI for secure mail is a big complicated thing.
Right, and so
people expect disk storage associated with mail.
Oh, sure.
And that now you're building a whole lot of functionality. Maybe not in the Nexus, but I have to trust it, and it's.
So again, it's the denial of service thing. The stuff, the disk, it's encrypted. Now you're right. The guy can erase it. There's a bunch of attacks he can amount that I don't get my mail, but the mail I send, nobody else. The wrong party is never going to get to see. And if I see it, it'll be right.
I can't attach stuff that I did on. If I prepared a document in Word, I think I have a hard time attaching it to the mail I send.
Yes, that's right.
The right-hand side doesn't have access to it.
That's right.
That's
all right.
Live in two worlds. Yeah. Now mail is a funny sort of thing.
Yeah. So actually, there was an internal joke about this, about what and internet messaging will be similarly less functional than.
Yeah, but most people don't send attachments.
We called for a while we called the IM messaging spook chat and the
spook chat.
This is the mail. Well, I won't say what we call the mail, but they were reduced functionality versions of the mail. That's right.
Nice to know you understand.
Now, actually, there are some interesting design things with the left-hand side and the right-hand side cooperating. So one thing you can do, so one way to think of secure mail is I'm going to do the whole email client on the right-hand side. And the obvious thing, just the net. Okay. Another thing is you have Outlook. It runs just the way it is. And when you get a secure mail, you take the part of the screen where the mail is displayed, say, hey, right-hand side, decrypt this for me and stick it up on the screen. All the UI is still run by the left-hand side.
But now...
You still can't run off it. You still can't.
So I compose mail on the left-hand side, and that virus that
I said display. Compose is a hard.
No. I run a script that controls Outlook, and it tells Outlook to tell the right-hand side to decrypt this mail over here and display it so I can screen scrape the contents.
No, you can't screen scrape.
On the left-hand side.
No. Okay, maybe I shouldn't have used the example. When I said Outlook says, here's a part of the screen, the right-hand side then owns it. Left-hand side doesn't have access to it anymore. It cannot screen scrape that portion of the thing.
Okay, but a fundamental thing about mail is authentication.
Yes.
And as soon as you involve the left-hand side, there could have been a virus that was either producing or consuming the mail that's being seen, and therefore the business case for secure mail just went away.
Let me carve this into two pieces, because composition is harder, because you want to use a probably sophisticated or composed mail. Let's just talk about mail display. Just mail display for a minute. The right-hand side, you could certainly be sure the mail was authentic on a right-hand side mail display. You can check whatever signature, whatever set of things you do on the right-hand side to make sure it was authentic, that it was confidential, all that would still work on the right-hand side. So you can imagine a situation where you were reading secure mail, but not sending it. And that's actually not too big a stretch, to tell you the truth. Anytime you introduce editing,
no, I want you
composing.
To think about this display example. So the email comes in.
Right. It's an encrypted block.
It goes to the right-hand side. It gets decrypted.
Right. Which model am I on, where everything's done on the right-hand side, the secure mail client's on the right-hand side, the whole thing? Okay.
So it goes to the right-hand side.
Right.
It gets decrypted. It gets displayed on right-hand side owned screen.
Right.
And now, can I store this?
You can store it decrypted. Encrypted, rather.
By
going to the UI and say, go ahead and store that. In fact, you could even, if the mail allowed it, we're starting to talk about rights management now, you can even give the guy the right, it would be dangerous, say, look, once you see the mail, if you decide you want to store it unencrypted and the left-hand side can get on it, go ahead. But you can control that by permissions on the mail.
But if the mail contains a Word attachment, you cannot...
You cannot read the mail attachment on the right-hand side of the Word mail. That's right. Or you can't run a movie on the right-hand side, the attachment on the right. You can't do any of that stuff. That's right. That's why it was a reduced functionality mail.
You also had a scenario where there was a kind of cooperation between the two sides. and the left-hand side asks the right-hand side to take over a piece of the window and display stuff that the left-hand side can't see.
Right.
I can believe that, but why can't the left-hand side pretend to call up the right-hand side?
Okay, so now you're asking, how do I know the screen is secure? The part,
Yes.
part of the, yeah. So there are a number of answers to this. Here's one, and when I talk about who do it. So the secure screen display has two components. One, it could be scraped, and the answer, you only authenticated stuff gets, sorry. You can never scrape a secure screen, right? So so the second thing is, why should I believe that screen is safe? That part of the screen is safe. And there are a few methods. It's an area where there has to be lots of work. But here's a simple thing to do. When you install your Palladium, this is mostly for the benefit of the user, the guy using the machine. So there's no reason to fake yourself out on this one. One thing is, when you get the Palladium machine, secure windows have a border, right? Some kind of border. And maybe what you do is you put the name of your cat. When you initialize the hardware in some way, in that border. And no other program has that secret. Well, no left-hand side program has access to the secret that's going to get displayed in the border. That's one way. There are more complicated, more sophisticated ways where, that involve more hardware. And again, we want to keep the hardware cost low. Maybe your mouse, when it goes over the secure screen, the hardware does something that indicates that it's the secure screen. But that would add cost.
But that would have to be secret also.
Well, no, it has to be in hardware.
Oh, okay.
It has to be in hardware, so you can't mess around with it. And the left-hand side wouldn't have access to it. Sorry.
What's required to enable these things?
Nothing. Once you boot the Nexus, I want to get to the Nexus boot quick, but you write an application, you can do any of this. Anybody can write any of these applications.
Right now, if this was in my computer, I would
You could go write an application, do this. You don't need us at all.
Somebody has to write it.
Somebody has to write it.
So right now, none of this is possible.
That's right. I'm sorry. So yes, it's a good point. So to use the right-hand side, you have to write programs for the right-hand side. Win32, I don't know how many APIs there are on Win32, but there's a lot. Like 15,000 maybe or something like that. Forget it. You're not getting any of those 15,000. You're going to get like 200 calls on the right-hand side.
200?
Yeah. Small.
200?
You think that's big? It might be 100. I don't know. I don't remember.
Like 20.
No, it's not 20.
After 20, it's not trusted.
Yeah, no, it's not 20. It's not 20. You have to schedule threads. You have to be able to do it. It's not 20. It's on the order of 100. It may not be 200.
This is what you are doing, or these are things that are possible?
Yeah, so I'm actually talking about both things. These are applications, some of which we will do, and some of which we'll hope other people do.
But so, could you...
But which ones are
rather than
at these,
replaying...
what are the priorities?
I mean, the popping up a level from Deirdre's question, the real issue is whether it's practical to write these programs, whether it's easy to write these programs, and whether they will force some kind of feature creep that will ultimately compromise your trust because of the size of the computer base.
And that's exactly it. That is the ultimate question. And our answer to that, which you might think is smarmy, is, you know what? You can write a big, bad bloated application on the right-hand side that you shouldn't trust, but you do. We're not stopping anybody from doing that.
So I have a different question for Microsoft.
The issue is, I mean, it's whether you do it inside or whether somebody outside does it. But we're interested in promoting secure solutions.
Yes. So Microsoft, okay, so again, you sort of have to factor. The Palladium is a platform, first and foremost, which means other people get to write stuff to it, not us. So now you're in the kind of like the trustworthy computing thing. Microsoft, maybe your point is Microsoft had better write secure applications, and they better watch out for feature creep in their applications, and that's right.
That was my question.
That's right.
That's right. So are you going to have an Outlook Express team that's going to be writing Outlook for the Palladium hardware as well as
in the first version? Okay, you're asking me. I haven't been canonized yet. I have a small group. They're going to pick a few small things to do. They're going to do it.
Like mostly. Office.
Huh?
They're probably going to do that.
Like who?
Like Office?
No, not Office. No, I do. Unless something that changed in the organization. I don't control Office. No, I'm not. Office is not writing those.
He's probably the top bullet on your list.
The first secure applications we will write. The first. Now that begs a longer question about what's going to happen. How is the rest of Microsoft going to participate? I can't answer that right now.
Someone can answer that, though.
Someday somebody had better not be able to answer that. I had better be able to answer that. And the answer actually would probably involve managed code, yes.
Okay.
Let's get back to the basics.
See, it's much more fun when people get to ask questions.
Yeah, but the questions are much better because they heard it.
Yeah, no, I agree. But one thing. So let me ask. I might take it back. I want some questions. I do want 5 minutes to describe the boot.
Yeah.
And after that, I'm gonna just let you go to.
Let me give you a segue.
Yeah.
So you explained a way to, in some sense, give the user the feeling that he's talking to his Nexus client agent.
Yeah, it better be a little bit more than a feeling.
Okay.
You better have some rational.
All right. So on the board that we had that secret protected by the hardware.
For example.
So you seem to have made a decision that that's cheaper or more effective or more secure than providing a separate device for the user to activate his Nexus and not the left side. In other words, you can get trusted fast with first hardware device.
Yeah, no, I'm sorry. When you activate the Palladium hardware, that's when you do all this stuff. There is a user activation procedure that activates the right-hand side stuff.
Separate device.
Separate hardware path which cannot be used by left-hand side software. Do not have access to. Does not have access.
So I have something special, either on my keyboard or some sort of a special.
So everything I just said would break down if the secret that you typed in for the border could be snooped by the left-hand side, for example.
So exactly. So you see what happens is over time your right-hand side is going to grow, and the guarantees you are going to provide that there is no Trojan horse in there to get your secret and leak it out through the channel decreases.
The major point, the meta point you make is an excellent one about bloat. Let me try to answer it. The hardware path for putting this secret in will never bloat. That will not bloat. And what we'd say is they fire John if the Nexus bloats. We would hold the line on Nexus bloat. Again, this is a platform and Microsoft will write applications. You can fire somebody if there's bloat in the applications at Microsoft. There certainly will be cases where there's bloated applications that users shouldn't trust. And we're not going to stop that. We cannot stop that. We won't stop that. You can know about it, but it's your judgment, not ours.
It seems that a better way to do it is to construct your trusted path for both input and output.
Trustworthy platform, not trusted platform.
Trusted path.
Yeah.
Trusted path, input and output trusted path, using a separate trusted device to your Nexus rather than primarily taking secrets on the board.
Well, we might want to take that one offline. So again, to the extent that you're using it in a trusted way, it is actually a virtually separate piece of hardware. It really is. The part of the thing that's trusted is virtually separate from the rest in some way. We do want, again, it's this ugly sort of economics thing. We don't want to add a lot of cost. Actually, I'll put it this way. I gave a talk like this to the CSOs, Chief Security Officers, and the comment I liked, it was great. It's the same problem with security all the time. Will people pay for security? Will they pay an extra blah to be safe? And I had this huge argument. So the change in cost to the hardware here that we're talking about is, for bill of materials, is, a few single-digit dollars. I won't say how much. And there was a guy from the bank who was giving me a hard time saying, well, people never pay for increased security. They say they will, they never will, never will. And finally, the guy from Boeing said they'll pay $5. They won't pay $50, but they'll pay $5.
Okay, well, my suggestion would be that you offer an option to build this trusted path, to have this as a separate option.
A hardware option.
A hardware option. To explain to people really what it buys.
Yep.
Because it does buy something that you are not producing now. In other words, you drew some lines in your designs and you said, economics tells me that this is the kind of security I'm supposed to provide.
Yep.
that you made that decision, but it seems that the user has a few options here that you might make actually money on that.
Yes. Well, first of all, we won't make money because we won't build the hardware. We have designed the system. Yeah. So I haven't talked about the hardware tech. We have designed the system so that you could actually add hardware and make it safer. For example, you could put a bus analyzer in the memory subsystem right now and read what's going on for right-hand side memory.
Let me rephrase this.
Yeah.
You have to be careful when you talk about trusted path of the input and output, exactly what you mean by
yes.
that.
Okay.
Because you put up some words in there, and the properties of those words are not quite clear.
Right.
So to clarify them, you have to tell them, look, there are degrees of trusted path. Here is what we provide. We provide this stuff as an option.
I agree. Well, if I tried to do this now, it would be an 8-hour talk.
No. You have to be careful because in the past, I'll tell you why.
Yeah.
We had a presentation on Palladium last time. I couldn't figure out if the errors that we've seen were the errors of design or the errors of presentation. Mm-hmm. Right? So we had the same thing yesterday with the Trustworthy Computing Initiative. There are errors in the presentation or errors of design. We can't tell.
Right.
So this is one of the reasons why we're asking questions, because we try to figure out you really know what the properties are, or you are ad-libbing.
Right. Well, so for actually the two parts of the system that are designed as in not done, not completely done, are trusted input and trusted output.
The last presentation, the crypto part, stack. Okay. I don't know how Brian or whoever did slides. Not very good that you have a super crypto group. Mm-hmm. I think you should go through them every time you do a presentation. We put slides, go through them, and they do a sanity check on them.
Okay. I don't think I mentioned the word crypto in this talk, but
not yet. But last time we had that.
Okay. Well, we'll see. You can tell me what to correct. Secure remote access is the second. I'll try to race through this because I can see. So right now, if I want to use a corporate application, Microsoft has to decide whether to trust my home machine. And to tell you the truth, they do. If I had a Palladium machine at home, again, they could have a secure remote desktop. I can use all my Microsoft applications. And when my 13-year-old, your 13-year-old, I don't know how old your son is, his worst games, his worst viruses can't interfere with it. So I have met my obligation to preserve confidential information, and secondly, I've given the user a way to trust that everybody else in his family isn't going to mess up the corporate jewels. And that is probably when we'll do the secure remote desktop. It's pretty easy to do, and that's a big hit, an easy thing to do. Again, the part of the economics is in a V1 thing. We're trying to walk a fine line between making everybody in the world rely on us, which is actually kind of bad. For security, you want to sort of burn in on stuff. And having it be valuable enough for people to buy. So we want to have valuable enough applications that the hardware gets taken up and there are ISVs and they build new stuff, but not try to make everybody do everything at once for a lot of reasons. Controlling the load, incidentally, is going to be probably the biggest thing. So if we try to make everybody do everything at once, it's just going to be brutal. But secondly, to the extent that everything is coupled, all security is on this one focal point right now. You can't, you delay it so long that it would be useless.
Is the expectation then that over time people will replace their current home PCs with this new
Yes.
machine?
So if you ask me,
in say 10 years, let's say.
Well, no.
Well, let's say N years.
Yeah, N years.
Everyone will have one of these kinds of things.
Yes.
Running both insecure and secure applications and switching back and forth, whichever. If they want security mail, they like to flip something.
Yeah, I wouldn't say insecure applications. All I would say is applications for which the security guarantee is different.
In particular, suppose a corporation mandated that its employees access from home only through the secure remote access, that all those employees
would probably have the machine, right? And so to answer your question, I would hope that every PC manufactured, I don't know, for years from now had this hardware. There's no reason to keep the price down.
Would it be then true eventually for all the little handheld devices that people use for accessing the corporate network or whatever?
Yeah and no. Again, really closed fixed function devices have a lot of the security guarantees I'm talking about anyway, right? Because nobody gets to load software in there. There's a little epoxy around the whole thing. It might not be worth it. Handhelds, as in your Palm Pilot, I actually do think it'd be a good thing. And I'm probably a fat client bigot. So I think those things will get bigger and fatter, and there'll be more stuff in it. And for the same reasons we want it on a PC, you'll want it on that. Yeah.
John, we're scheduled for a break very soon, so I'm going to suggest that you finish this slide and then we take...
Actually, can I finish the next slide too, because they're in a sequence, and then we'll break.
Okay.
And we'll come back and we'll do the boot.
And maybe this will have the effect of attenuating questions, because I'll bet these people want to have a break soon. Yes.
I don't know, they seem to be on strong to me. The next thing you can do is use Palladium as a network guard. So, again, you can run anything on your machine, but, for example, somebody who wants to talk to you on the network may say, you know, I want to talk to your Palladium monitor that looks at your machine. I'm not going to let you on my network. You can do whatever you want on your machine. I'm not going to let you on my network until the software on Palladium software I trust has looked at your machine and make sure it conforms with whatever I believe it should conform with to get on my network. And vice versa. I mean, it's a two-way authentication thing. It's actually part of secure machine policy. An organization can not lock down their machines. They can't force people to boot the software they want, but they can say you're not getting on the corporate network unless you do what I say, which has an interesting sort of bifurcation. It means that people can leave. And gives the IT guys a little bit relief when somebody says, I want to run wacky application 37, and they say, absolutely not. You can only run the 3 applications I say, and that's it. So you can still do that, but you can say, hey, look, I'm not going to be on the network when you do that, and you can check that I'm not doing anything wacky when I'm talking. Okay, and this is the last one. And actually, this confidentiality enforcement, yeah, you get that. That's not the secure audit, all that stuff. Okay, then small rights management. So I wanted to get to this slide because rights management always starts off a controversy. It's good to get it over with quickly. So there's what I would call small rights management. And small rights management means I'm protecting stuff within a small group. So corporate documents. Another example of what I'd call small rights management is when I buy books from Amazon, they keep information about me so they can sell me the next set of books. And they have that information. They decide to change their privacy policy. They can publish it to the world. There's nothing I can do about it. I could actually say, hey, look, I'm going to let your application see so you can make me buy the next 8.5 books published. But that's secret information, and nothing but that application can get it, and can only use it for the purpose of advising me about books, and that's it. Another version of small rights management is all the protect your medical records, blah, 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 that sort of stuff. So hardly ever anybody has an issue with small rights management because it's mostly privacy protecting. Yes?
I'm sorry, I want to focus on that Amazon question.
Okay.
Rather, I can do it after the break.
Why don't we do it during the break? You and I can.
Okay.
Yeah.
No, we want to hear that.
Oh, all right. Well, then.
Stand next to him during the break.
Ooh, that's good. Okay. So the second one is big rights management, and that's to protect, books, movies, audio, software. So let me go through the line here. She's already quivering. First of all, I think big rights management is a good idea for 2 reasons. One is, for purely selfish reasons, I don't want PC locked out of premium content. And the whole idea of big rights management is just make sure the PC is not a disadvantage. Just, take off the table whether you're as safe as the DVD player. Incidentally, DVD players are not that safe. Incidentally, if you use it for big rights management, the content's going to leak. In fact, you use anything for big rights management, it's going to leak. Doesn't matter what you do. The whole idea for big rights management for Palladium, for a Palladium application, is just to make sure the PC is as good as anything else for using content people want to protect. Also, I think it lets you do more flexible things than you do with current rights management. So, for example, it's kind of a big problem in device-based rights management because you buy a copy of Gone with the Wind and it only plays on one player. When the player breaks or you buy another one, you can't, because of the way the protection is done, you can't use it on that. Well, this is a flexible enough system where, in a purely trusted way, you can say, okay, any new trusted device you buy, or any new Palladium computer, incidentally, that you buy, you can play the content. So it has a very nice usage model. You don't have to go back to the content owner and ask permission, in principle. You just get to use it. You can also manage your protected content in a much better way. And I have to admit, I'd like to put my entire library on the PC. And then when I'm on the road and forget a critical part of the proof, I don't have to scour, find the local library, which won't have a copy of the book the proof is in. I can just go to my home library, remotely, look up the thing, get the proof, and I'm a happy guy. Probably most people, it's more like they want to listen to the Madonna song they left home, but there you are. So I actually think big rights management is an important use. I don't. This is typically the controversy Microsoft gets in, or we get in, is would I say it was the use for Palladium? I'd say absolutely not. Would I say it was a primary use? I'd say it was an important use, a major use. I wouldn't say it was.
Is that a use that is likely to be supported in the first version?
So the answer is kind of yes and no. I don't think we'll have a protected media player in the first version. So for songs and, for audio and video, probably not in the first version. Incidentally, audio and visual are also small rights management if you're doing a corporate. Okay. For the books, I guess not also, but in principle, if we have any secure viewer on the right-hand side, you could display secure text. I guess.
The question I wished I had asked is maybe at the end you would go back through the four categories
and say what we're going to do.
Which you think is destined for the first release and which is for the subsequent.
First of all, let me just warn you, it's always a changing thing that depends upon resources. Always. But I'll tell you what I think. I'll tell you the top 5. And we'll probably end up doing 3 of the top 5.
Well, I mean, if you sell us, then maybe we'll write a strong argument for you to get more business.
Ooh, okay. Can I have an extra 10 minutes during the break? I have a little thinking to do. Okay. So anyway, that's the rights management. The rights management software can be as good as possible. It means it can be as privacy protecting as possible, all that stuff. But it's up ultimately to the content owners to write reasonable policies that will let consumers use it in a reasonable way. Otherwise, all bets are off. And my guess is consumers will say, you can take your big rights management and do something bad with it. So, and then secure collaboration. I'll focus on the online game application because it's an interesting scalability argument. So I'm told your son probably plays games. Collaborative games apparently suffer from. Well, I know they suffer in principle from it, but apparently they suffer in practice. If you want to do a game where there's no cheating, the server has to make sure there's no cheating, right? And that introduces a scalability issue. It also introduces, no offense, a way for Sony to make money, or perhaps Microsoft by saying, I don't know any other way to do this unless you subscribe to a subscription service and do this. Well, so now you have client enforcement of rules. So in principle, two people can have a secure contract negotiation, play a secure game without involving a third party. Okay, so I think following Fred's advice, we'll have a break now. Thank you.